Uh, Hello, I'm Kim Hyun-chul, a first-year integrated master's and doctoral student in Professor Ho-Seok Park's laboratory at Sungkyunkwan University's Department of Chemical Engineering. Although I have limited research experience as a first-year student, today I will explain my current research areas. I am conducting research on inkjet printing based on two-dimensional materials and energy storage devices. So, my presentation title is Two-Dimensional Material Inks for Performance Improving of Energy Storage Devices. This is my presentation contents. I will present in the order of two-dimensional materials, printing techniques, and application of two-dimensional material inks. Graphene is a representative 2D material consisting of carbon atoms arranged in a flat structure, with the advantage of excellent electrical and thermal conductivity. The current 2D materials being inked is MXene, which can be applied to electronic devices and energy storage systems due to its high electrical and thermal conductivity. Using MXene as an electrode material can improve the charge and discharge speed of energy storage devices by increasing the mobility of charge and enhancing performance. In addition, it has high chemical stability. There are plans to attempt ink-forming black phosphorus in the future. Black phosphorus has high electrical conductivity and high electron mobility, making it suitable for application in electronic devices and energy storage systems. Due to these characteristics, black phosphorus is gaining attention and as an important material that can pioneer new application fields in future electronic devices. The picture on the left is a synthesized MXene SEM data. When compared to the ideal MXene SEM data on the right, there are parts that appear to be multi-layered. But I need single layer, so I have to delimitate it. The synthesized MXene has analyzed spectrometrically using XRD. The chemical formula of the theoretical MXene is Ti3C2, and the synthesized MXene showed similar XRD data to the theoretical MXene. The elimination process is a machine process for inkjetting after synthesizing MXene. The reason for the elimination is to obtain a single layer. Firstly, by coating ink in a monolayer, a more accurate and consistent thickness and texture can be maintained. When coating in multi-layers, problems can arise at the layer interfaces, resulting in non-uniform thickness and texture. Secondly, less ink is required when coating in a monolayer. When coating in multi-layers, the amount of ink increases with each layer, resulting in overall great ink consumption. Additionally, when coating in multi-layers, the printed color becomes darker, requiring more ink to achieve the desired color. Therefore, by coating ink in a monolayer, a more accurate and consistent printing quality can be maintained while reducing the amount of ink consumption. Most people are familiar with 3D printing. These are currently the most commonly used printing techniques. Screen printing is another mass printing method that allows pattern design. Considering that many as prepared 2D inks have low viscosity, binders are typically required. Screen printing allows fast operation. The modified printing system in flatbed, automated, and roll-to-door modes can have a speed of 70 10 milliminutes. The development of ink that has the right viscosity without the need for binders is needed to eliminate post-treatment and preserve the functional properties of 2D materials. It has high throughput, high compatible with various ink and substrate, but relatively high prototyping cost. As a direct ink writer technique, inkjet printing can accurately deposit inks through digitally controlled ejection to form pattern in a material conserving way. It can also generate 3D structures. However, achieving high-quality inkjet printing is challenged because the deposition process is largely affected by ink parameters and printing conditions. It tests digitally controlled direct writing, minimal material wasting, high prototype cost, but relatively complex ink formulation through low throughput. The outstanding solution processability of 2D materials enables the easy and scalably manufacture of electrode and devices with desired geometric contribution on various substrates. The advantageous properties of 2D material inks are exploited in a wide variety of applications, including energy storage, sensors, electronics, optoelectronics, and bioengineering. I am planning to apply two-dimensional inks to energy storage devices. Electrochemical energy storage devices, in particular supercapacitor and batteries, are essential in our daily life. However, commercial devices suffer from limiting power of energy density or limiting power or energy densities and thus struggle to meet the the ever-increasing performance demands of arising technologies. 2D materials bring new prospects to this field,
Their 2D layered structure results in more exposed active surface and richer ion transport channels for electrochemical reactions compared with their bulk counterparts, and their solution processable nature enables large-scale and customized devices manufacturing. This is technology readiness level of application using 2D inks. As mentioned before, I have a plan to conduct inkjet printing of black phosphorus or 2D materials in the future. The reference listed above are the one of ones used to create the presentation. Thank you for your attention.